Hey, welcome back. This is part 2 of our lesson on harmonics for standing waves with fixed ends for instruments like guitars as an example. So if you didn't get a chance to see my previous screencast on this, I'm going to put a link in the upper right as this is a continuation of that. Alright, let's go ahead and get to it. We're going to talk about something called harmonics. I'll define that in just a moment, but I do want to talk about here we've got a fundamental frequency. First of all, this is going to be the first case where we can logically have a standing waveform. And this is the pattern in which you see when you have a wave with two fixed positions, this is the lowest frequency you can have, or the greatest wavelength you could have, that will form a standing wave. And this is the shape that it forms. Now notice this is really like 1/2 of a wavelength right here. In other words, if I continued this out, this would only be half, and then we would have it come over here. The reason why you see it like this is you have 1/2 of the wave and then it bounces, comes back, and these are constantly interfering with each other, and that's how you're able to form that wave. So the very first standing wave that is possible is called the fundamental frequency, or oftentimes it's just called the fundamental. And so if you think about what the equation would be for a fundamental, if we said this length right here is going to be our L value, L will represent this entire length of the string right here. We could say L is equal to 1/2 of a wavelength. Why is that? Because this is only 1/2 of a wavelength, like the crest over here and the trough would be over here, that kind of thing. So it's only really 1/2 of the wavelength. You will need to be able to write equations like this eventually, and we're going to practice this to say like length is equal to 1/2 of the wavelength, because typically you'll know like the length and you'll have to figure out what the wavelength is, or vice versa, one of the two. Alright, let's take a look at what's called the second harmonic then. And so the second harmonic is going to be the next octave up. If you are a musician or have any musical training whatsoever, then the next octave up is going to be the second harmonic, which is exactly doubled the frequency for the first harmonic, or the fundamental frequency over here. And in this case, you can see that you've got your length down here that corresponds to this length right here. That is going to be equal to a wavelength. And this is easier, I think, to understand than the very first example I gave you. It just works out that way. But I think you can see that this length right here is exactly equal to the wavelength of this standing wave. And so if you can write that out, length is equal to wavelength, then you're going to be good for a lot of these problems. Alright, third, let's take a look at what the third harmonic would look like. It would look something like this. And so you would take this frequency and you would multiply it by 3 to get the frequency for the third harmonic. We also would say, well, this entire length is equal to 1.5 wavelengths, or 3/2 of a wavelength for the third harmonic here. And can you guess what the fourth harmonic is going to look like? What its frequency is going to be, what the shape will look like, and what the equation will be. And so I'm going to ask you, using this pattern, try to guess what this is going to look like. Okay, and so it's going to look something like this. So the fourth harmonic as a frequency is going to be 4 times our fundamental frequency. And you can say, well, this entire length is equal to 2 wavelengths, right? And if you look at the image, I think that actually does make some pretty clear sense. As long as you can write this equation, then you're going to be able to solve a lot of these problems. And this is another case where I think drawing a diagram will really help you to understand what's going on here. Alright, and I have used the term harmonic, but I haven't really defined it yet, so I'm just going to throw this out here and say that a harmonic is a wave with a frequency that is the positive integer multiple of the frequency of the fundamental frequency. Now at this point, I think this can make sense to you, now that you've seen the example. So let's take a look at this again and say the harmonics are the waves with frequencies that are integer multiples of the fundamental frequency over here. So if our fundamental frequency is 440, these are all integer multiples of that. Hopefully that now makes a little more sense. Okay, and so here is a skill, again, that you're going to need to be able to master to be able to solve problems like this. And my question is, how many wavelengths do you have in this L value? This L value right here would be the length from one fixed position to another fixed position. How many wavelengths do you have? And hopefully you're able to come up with, well, here's half a wavelength, right? Here's another half, and a third half, and a fourth half. So 4 over 2 is 2, and that means there are 2 full wavelengths here. Alright, how many wavelengths do you have in these L values? So come up with an equation of your L value is equal to how many wavelengths for each wave animation. So let's do the first one in your mind right now. All right, well that's going to be L is equal to 1/2 of a wavelength. How about this one over here? L is equal to what? Well, L is equal to 1 full wavelength. How about this one over here? L is equal to 1.5 or 3/2 of a wavelength. How about this one over here? L is equal to 2 wavelengths, or you could say 4/2 wavelengths. That reduces to 2 wavelengths over here. How about this one over here? Okay, so that's going to be 5/2 wavelengths, or 2.5 wavelengths. How about this one over here? L is equal to 6/2, or 3 wavelengths. And if you can write out this equation right here, then you can do a conversion later and solve problems with it. All right, and lastly, I do want to go over an equation for standing waves on a vibrating string, like if you're working with a guitar as an example. So the frequency of the wave that you're going to be working with is equal to the harmonic number. Now that could be like an integer value. So if it's the fundamental frequency, it's going to have a harmonic number of just 1. If it's the second harmonic, then it would have a harmonic number of 2, and so on. Work your way up. And then this V value has to do with the speed of the waves. The L value has to do with the length of the vibrating string. And so the question is, what is the fundamental frequency of a guitar string when the speed of the waves on the string is 119 meters per second and the effective string length is 65 centimeters? All right, and this problem's actually going to be really straightforward. In fact, it's already isolated for us, so at this point all we have to do is plug in. So just think about what numbers you would plug into this equation for a moment and how you could write it out. Okay, and so hopefully you're able to do this. If we're talking about the fundamental frequency, that would mean the harmonic number is just going to be 1, and the wave speed is given to us. The 2 is down below here. The length down here is in centimeters. You're going to convert that into meters, and you just do the math, and you end up with an answer of 91.5 hertz. So hopefully that's been helpful. I'm going to do other lessons in this unit and other units as well, and if you have any questions down below, please let me know, and I hope you all have a great day. Take care.